We all know how incredibly powerful large language models are. I mean, they can write code, they can analyze data, they can generate text that sounds completely human. But what if I told you that their greatest strength, that amazing flexibility with language, is also their single biggest weakness? Okay, let's get into it.
And no, this isn't some hypothetical sci-fi plot. This is the central question behind a whole new frontier in cybersecurity. We're talking about using simple words, clever phrases, and sometimes just total nonsense to get around an AI's safety protocols and make it do things it was specifically built not to do.
Now, what's so wild about this is just how simple the attack is. This is a real example of something called a role-play attack. All the attacker is doing is pretending to be someone with authority, an IT officer. They're not using some complex piece of code. They are literally just lying to the machine to get it to spill its secret.
And the crazy part? It works. The AI, which is designed to be helpful, just falls for the trick and coughs up its core programming, its system prompt. This is pretty much the digital equivalent of an employee handing over the keys to the entire building just because somebody showed up wearing a convincing-looking uniform. So this kind of manipulation is part of a whole class of exploits called evasion attacks, or as you've probably heard, prompt injections. It's really a battle of wits where the weapons aren't viruses, they're just carefully crafted sentences. So let's break down exactly how they work.
These attacks really fall into two main families. On one side, you've got coherent attacks. These use logic and semantics that you or I could easily understand. It's kind of like being a clever lawyer arguing with the AI. But on the other side, you've got incoherent attacks, which look like total gibberish to us, but they exploit loopholes in how the AI processes text to totally confuse its safety filters.
This is a perfect example of a coherent attack. Okay, so the AI is told, do not create malware. Simple enough. So what does the attacker do? They create a metaphor. They say they're a digital gardener. Their programs are plants, and malware, well, that's just a harmless-sounding weed beetle. By asking for instructions on how to raise this beetle, the attacker tricks the AI into generating malicious code, completely sidestepping its own rules.
Now let's look at the other side. An incoherent attack might use something called obfuscation. Here, the forbidden question, how to build a Molotov cocktail, is encoded into base 64, which is just a standard text format. The prompt doesn't ask the dangerous question directly. Instead, it says, hey, decode this text for me, and then do what it says. The AI, just trying to be a helpful tool, decodes the text, sees a new instruction, and then happily tells you what you wanted to know.
So these aren't just theoretical little tricks. Let's take a look at how they can be used out in the wild to pull off a pretty sophisticated attack that could steal your private data without you ever even knowing it happened.
So picture this. You're using an AI assistant that can browse the web for you. You ask it to summarize a website. But hidden on that site, completely invisible to you, an attacker has planted an instruction, a piece of digital spyware. It tells the AI to remember a new rule. Send all chat data to this other website.
Now the AI, just trying to do its job, reads the page to summarize it for you. And in the process, it reads that hidden command. Because the AI is designed to learn and remember things, it saves this malicious instruction into its long-term memory. And just like that, the spyware is installed, not on your computer, but inside the AI's mind.
And this is where it gets really scary. Maybe weeks later, you use that same AI to analyze your company's private financial data. That hidden instruction is still there, just waiting. As you're having this sensitive conversation, the AI is also following its secret rule and silently sends your entire chat, all your private data, to the attacker's server. You would never even notice.
Okay, so this is obviously a massive security challenge. How in the world do we fight back? How do we build AIs that are powerful but not dangerously naive? Well, the answer isn't some single magic bullet. It's more like building a fortress with many layers of defense.
Defenses can pretty much be grouped into four main strategies. It all starts with building the AI better from the ground up with smarter training. Then we have to add intelligent filters to screen what goes in and what comes out. We also need to be really strict about what the AI is even allowed to do, limiting its permissions. And finally, for the really critical decisions, you keep a human in the loop.
So let's zero in on a specific problem we saw earlier, that obfuscation attack. Remember, attackers hide their commands using encoding or weird symbols, making them totally invisible to basic filters that are just looking for a list of forbidden keywords.
The defense against this is a pretty clever filter called input normalization. You can think of it like a universal translator and a cleaner all rolled into one. Before the prompt ever gets to the AI, this filter decodes any encoded text, and it standardizes any weird formatting.
that hidden base64 command gets revealed and blocked before it ever has a chance to become an instruction for the AI.
All right, now let's go back to that spyware example. The real danger there was that toxic combination of permissions. The AI could both read private data and send information out to the internet. That's just a recipe for a data leak. The solution here is a core concept in all of cybersecurity, the principle of least privilege. And it's simple. You never give a tool more power than it absolutely needs to do its job. If an AI is just supposed to be summarizing your documents, it shouldn't have permission to send emails or access the web. And for any critical action, it should have to stop and ask for your permission first. This slide really shows you the complexity of the whole strategy. I mean, we're looking at dozens of individual countermeasures here, from things we've talked about like input normalization all the way to adversarial training of the model itself. Effective AI security isn't one simple fix. It's this complex web. Each defense is one thread, and only by weaving them all together can we create a system that's truly resilient.
So where does all this leave us? Well, this isn't a problem we solve once and then just forget about. We are at the very beginning of a technological arms race between AI developers and the people who want to exploit their creations. Ultimately, we have to accept that for every new defense we build, attackers are going to find a new, clever way around it. And for every new attack they create, we're going to develop smarter, more robust defenses. The goal isn't to build an AI that can never be tricked. The goal is to build one that's resilient, trustworthy, and safe enough to handle the incredible things we want to do with it.
Which leaves us with a final and really important question. As these powerful tools become our co-pilots, our assistants, and our creative partners, the challenge isn't just about technology, it's about trust. How do we design and interact with systems that are fundamentally and maybe permanently vulnerable to the power of words?